Okay, so now we go to the last application that we want to focus, which is about the local extrema. So in this section, we want to implement the partial derivatives to determine the maximum point or the minimum point that you have in the surface. Okay, the idea is, let's say you are given just a random surface. Okay, then using the partial derivatives, so you can see that there is some slope, right? So this is it. So the function given to you is a two variable function. Should be two variable function. Okay, so now you want to know, is there any maximum or minimum point on that surface? So let's say without sketching the graph, because sometimes the graph is quite complicated to be sketched by hand, or the idea is, without sketching, how can you determine there is a maximum or minimum point on that specific region? Okay, but because of the surface sometimes is very large, so we just focus on the local area, so on some specific region only, not for the overall surface. So that's why we can say local extrema, because another application we call that as a global extrema. Okay, but then that one is not part of our discussion for this course, so we only focus on the local extrema of the two variable function by using partial derivatives. So in this case, sometimes another word of local, we call that as a relative extrema, and the global one is called absolute extrema. So absolute extrema is not part of in the syllabus. Okay, we just focus on relative or local extrema. Okay, so as we know that the word of extrema, there is a maximum or minimum. Okay, so now the idea is without sketching, so we want to investigate where is the maximum or minimum value or minimum point of that particular surface. Okay, as you can see here, if you have the shape is something concave down, and you should have the maximum point or maximum value. And for minimum, if you have a concave up, and you should have the minimum value or minimum point. But if you have this kind of shape, if you just watch from this side, from X, okay, when you see from X, you are looking from X, you're sitting over here, and you can see minimum, right? You can see this curve, so you can have minimum. But if you move around and you're sitting along the Y, so you can see this one, this U-shaped concave down, and it is like maximum. So there is the maximum and minimum on the same point, so we call that as a saddle point. Okay, so what is a saddle point? Saddle point is surface that curves up in one direction and curves down in another direction. So when we join them, so we have just like a saddle curve or mountain pass. Okay. So meaning that there are three possibilities. You can sometimes have a maximum, or you can have minimum, or not maximum, not minimum. So we call that as saddle. So how do we find the local extrema? So firstly, so this is the step. Okay, so what you have to do is, firstly you have to differentiate partially the f respect to x and respect to y, and then you have to equate that by 0. And then you solve for x and y. Okay, so when you solve this simultaneously, then you can have the critical point, so or stationary point. So then after you get the stationary point or critical point, so you have to determine the behavior of that point. That point can be maximum, that point can be minimum, or can be saddle. So in order for you to determine that, you have to apply a test. You have to obtain a test where the test is namely a second derivative test. Why we call that as a second derivative? Because from the formula, so this is the second derivative test. You have to apply the second order of derivatives. You can have the second order of x, you can have the second order of y, and you can also have the mixed partial between x and y. Okay, so this formula is actually from the Hessian metric. So it is a metric which is named as a Hessian metric, where the component of that metric there are second order derivatives. So Hessian metric, or in this case they put that and G, or sometimes they put H. So the metric G is, so the component is this just 2 by 2 matrix, which we have, if you have two variable x and y. So the first component is you have fxx, and then fxx, and you have yy down here, and then for this one the component is fxy, and this one fy. So this is a Hessian matrix, but the determinant of Hessian matrix will give you the formula of this test. So you know the formula of determinant. So how to obtain the determinant of the 2 by 2 matrices? So the determinant, is, so actually this one is Hessian matrix, okay, in terms of xy. But if you want to get the determinants, it's transformed into G, where the formula is, you have to just cross, you have fxx multiplied by fyy minus fxy fyx, and because of fyx and fxy they are the same, so we can simplify. We have xxyy minus fxy or fyx and to the power n squared. So that is the formula. This is called as a second derivative test. So from the result that you obtain, you can determine that the stationary point or the critical point that you obtained just now is maximum, minimum point, or saddle. Okay, so how can you know that? So there are some tests that you can follow, which is this one. Okay, so by using that, so I will use this G. Okay, so G, if it is positive, okay, so your G, if it is positive, so you have positive, or you can have negative, or you can have 0, right? So if it is positive, so then you have two possibilities, max or min. Okay, and if it is 0, so no conclusion, so your test failed. So no conclusion. So you have no idea, then you have to refer to the graph. Okay, so meaning that the test failed to tell you something about the outcome. So you have to just maybe use another theorem or formula, or you have to sketch. But in this, because our scope, you just use this second derivative test, so meaning that if the test fails, so the test failed. Okay, but then it should be referred to the graph itself. Okay, but if you have the G is negative, so meaning that you can have saddle. So what is that saddle looks like? So in some direction you can see max, in some direction you can see min. So you have a saddle shape. So that is called saddle. Okay, so now let's say your G is positive. Now how can you determine the point is max or min if your G is positive? So you have to refer to your fxx value. fxx. What is fxx? fxx is the first component on the Hessian matrix. So if your fxx is positive, so if it's positive, so this one, if fxx is positive, then you have minimum. If your xx is negative, then you have maximum. Okay, so that is the condition. After you implement the second derivative calculation, you obtain the g and you have to investigate the value. But if your answer is positive, so you have another condition to tell you that the point that you have is max or min. So how can you know that? Then you have to refer to your second order with respect to x. Okay, so normally how can you easily remember or memorize this condition? How can you say that? Sometimes you'll be confused, okay? Just mix up everything. How can I say, okay, I have the g is positive, so which is which? How can I determine the critical point that I obtain is max or min? Yeah, I know that you have to refer to f of x, but then how you know if f of x is negative, so you have max or min? It's sometimes a bit confusing. So for me, how can I memorize that? I will relate this with something nature, something our real, something in the reality, right? So how can I use that? So this is f of x. So you have positive, just like you receive a positive news, a good news. So you feel happy, right? So when you feel happy, so you will just like this, smiling. You are smiling. You are smiling, right? So when you are smiling, so you should have the U shape. So you should have a minimum. So your critical point something minimum because you are smiling. Okay, you are smiling. Okay, but if you feel bad, if you receive a bad news, so you feel sad, right? So so how your face when you feel sad? So you have something like this, right? You feel sad. You feel very upset. So your face is like that. So you should have something maximum there. So that's the way I share with my student. And actually, I got this from my lecturer about 30 years ago. So I have my lecturers share this with me, with my classmates. So I still remember that it is very easy, easy thing to be memorized. Yeah? So I hope that you can implement this when you are doing the second derivative test as well. Okay. So that is the condition. Firstly, you have to find out the critical point first, and from there you have to investigate whether the point that you obtain max, min, saddle, or the test fail. So it should be referred to this condition. Okay, so in order to understand that, okay, so we look at the first example here. So find the critical point, so that is must. Without critical point, you cannot determine whether that point max, min, or saddle. Okay. So find the critical point of the given function of the variable and determine the nature of this point, whether it can be local, it can be minimum, we have a relative minimum, a local minimum, or local maximum, or saddle point. Okay, so now we want to work on it. Okay, so the first one, your function is f x y. 2y cubed minus 6xy minus x squared. Okay, so first find the critical point. So how to obtain the critical point? So your critical point can be 1, 2, or more than 2. You can have more than 1 points. So you have to differentiate that, find out the fx. So negative 6y minus 2x equal to 0. Fy 6y squared minus 6 equal to 0. Okay, so just check fx. Fx negative 6y, negative 2x, fy 6y squared. Okay, so you have to solve this simultaneously. Okay, so it looks like from this you can have 2x equal to 6y. So x is equal to minus 3y.
Okay, and we substitute this into this equation. So you will get 6y squared minus 6 minus 3y negative equal to 0. So you have 18 y equal to 0. Okay, so now we have this. Okay, so next we can solve for y, right? Okay, I know that some of you like the cancel, right? So, but you cannot just cancelling out directly. You have to factorize first. So factorize the y. So you will get 6y plus 18. Then you can have y equal to 0 and 6y plus 18 equal to 0. Then you will get y equal to negative 18 over 6 will give you minus 3. So you got two values of y. But if you just directly cancel out, so I know that you like it, right? Just cancelling directly, you will give me 6y plus 18 equal to 0, and you just get single y, which is this. Your answer is not complete, it's incomplete. But because of, you have to, the correct way is you factorize the y first, then you will get two values of y. So since you got two values of y, when you substitute your y into this equation, so you will get x equal to 0, and for y equal to minus 3, so your x is minus 3 minus 3, and you will get 9. Okay, so now you can say that the critical points are 0, 0, and 9 minus 3. So that is your first task. Obtain the critical point. So next we want to see the nature. We want to investigate the behavior of these two critical points, whether they are maximum points, minimum points, or saddle points. Okay. So now let's say, but before you proceed with to determine the behavior or the nature of these 2 points, you have to obtain the g first. What is g? So g is the second derivative test. Okay, so g is fxx fyy minus fxy squared. So we differentiate the f with respect to So we differentiate f with respect to x, so this one just becomes minus 2, and differentiate y with respect to y, so this one becomes 12y, and then we differentiate x with respect to y, and we have minus 6. Or you can also differentiate y first and then differentiate with respect to x, so you will get the minus 6 as well. Okay, now by using this, we plug into the g formula, so you will have minus 2 12y minus 6 squared. Then you will have 144y plus 36. Okay, so now at 0, 0. So what is the nature at 0, 0? So investigate your g by plugging in your values of y here. Okay, in this case, your g is in terms of y. Is it always in terms of y? No, it can be constant, or it can be expression in only x, or it can be expression in terms of x and y as well. So not always in terms of y or constant. Okay, so now because you have only y, you will just focus on the value of y. So you have 36. Negative, right? Negative. Okay, so you have negative. So what can you say about the critical point at 0, 0? So you can say that 0, 0 is a saddle point. Okay. So next, at the second point, 9 minus 3. So what is your g about? So we substitute the value of y minus 3. So minus 3 minus 36. And the answer will be positive. So it can be max or min. So you have to look at your fxx. Your fxx is always negative. Just coincident, okay? It can be in terms of y or in terms of x. Okay, so this is negative. Fx is negative. So if you feel bad, you feel upset, you feel sad. So how does, so what is your expectation when you receive a bad news? So you will sad, right? So when you feel sad, so fxx here is negative. So you feel sad. You feel sad. That is your face looks like. And we supposedly the 9 minus 3 is maximum. So 9 minus 3 is a maximum point. Okay, for x and y. That is called maximum point. But let's say they ask, then what is the maximum value? So how can you determine the maximum value? So maximum value here is the value of the function itself. If they're asking for it, okay, if they ask, okay, evaluate the maximum value based on the maximum point that you obtain. So you just plug in the xy value into this equation. So just now your equation is, so what you can do is, okay, use this value. So what is the function that we have? Okay, so we just substitute. So to get the maximum value, if they ask for it, okay, maximum value. So how to get that? So you just substitute 9 minus 3 into your function, your original function here. So you will get 2 minus 3 cubed minus 6, 9 minus 3. And then minus 9 squared. Okay, then when you evaluate that, so you will get 27. So you know that you will get 9 at 9 minus 3, it is a maximum point where the maximum value is 27 if they ask for it. But normally, they're just interested to know the point only. But sometimes they will ask for that. Okay,